Embeddings are not a free upgrade over BM25. We'll compare sparse and dense retrieval by query type, so the winner is based on metrics, not assumptions. This is the workflow you'll know how to run when we're done, which compares sparse and dense on query slices and picks the lead retriever using NDCG. I'm Professor Pi, teaching search and IR with simple Python. Search teams face a common question. Do we replace term matching with embeddings everywhere, or combine both? The pain is real. IDs and model numbers need exact matches. Product descriptions and user intent need meaning. Success looks like fewer misses, lower support tickets, and measurable ranking gains on the queries that matter. We solve that by measuring, not guessing. At a high level, sparse retrieval means matching terms we see in text. Dense retrieval means matching meaning via vectors. Think of sparse as exact keys, and dense as a translation into a shared language. For a quick intuition, imagine an order number and a symptom description. The number should match exactly. The symptom should match meaning, even if the words differ. We will build a tiny pipeline that shows both behaviors on the same small corpus, slice queries by type, and score each retriever with NDCG, which is a ranking metric that rewards putting relevant items early and discounts lower ranks by a log factor. The goal is to see which retriever wins on which slice before choosing a per-query rule. Now we'll create the tiny corpus and run an exact lookup. This snippet creates a tiny corpus and demonstrates exact term lookup on an ID-style query. The list named docs holds short human-readable items that include an order number, product names, and a route ticket. The function exact takes a query and a list of strings, lowercases the query, and finds the index of the document that maximizes substring matches with that query. Using count inside the key function provides a simple yet dependable scoring rule for exact tokens, like numbers or codes. We then call exact with the query 784512 and return the best matching document. The printed title confirms that a pure exact term can reliably find the intended item first, which is exactly what you want for order IDs. Next, we'll score the same corpus with a sparse BM25 style model. This code builds a lightweight BM25 style score and uses it to rank the tiny corpus. The set vocab collects lowercase tokens across docs. Then IDF uses math.log to compute inverse document frequencies for each token. The function BM25 scores a document by summing IDF-weighted term frequencies with a length normalization using the average document length A. The query queue is tokenized similarly, and Max picks the index with the best score. Using a real IDF improves robustness versus raw counts, especially when common words would otherwise dominate. Increasing the length penalty would further favor short, precise matches. The printed title shows a strong sparse match for medical strength terms, which highlights how IDF steers the ranking away from stop words. Then, we'll show a tiny dense retriever using handmade embeddings and cosine similarity. This example introduces a tiny handmade embedding to capture synonymy and retrieves by cosine similarity. The dictionary E maps words like ibuprofen, Advil, pain, and headache to short 3D vectors that roughly align analgesic terms. The function embed averages vectors for tokens present in E and returns a zero-like vector when nothing matches, while cos computes a normalized dot product between two vectors. We embed the query headache relief, then rank documents by cosine to that query vector. Because Advil and ibuprofen align with pain and headache in E, the relevant analgesic document scores highest. The printed title shows dense retrieval surfacing meaning despite missing exact words, which is the core promise of embeddings. Next, we'll compute a formal quality metric to compare rankings on a synonym-heavy query slice. This snippet measures how well each retriever ranks a synonym-heavy query using NDCG at cutoff 3. The helper rank sorts scored pairs and returns top indices. We compute dense scores via cos with embed and sparse scores via BM25. The relevant set rel includes both painkiller documents, reflecting acceptable answers. The function NDCG uses math.log2 to compute discounted cumulative gain and normalizes by the ideal ordering, returning a value between 0 and 1. Increasing k would reward retrieving more relevant items deeper in the list. The printed dense and sparse NDCG values directly show which retriever handles synonyms better on this slice, letting us quantify the gap instead of guessing. Finally, we'll implement a tiny routing policy that picks sparse or dense per query and then evaluate it. This code implements a tiny routing rule that picks a retriever per query and evaluates the policy. The lambda choose returns sparse when it sees digits or hyphens that signal IDs or model numbers, and dense otherwise. The function run applies the selected method. It ranks documents with BM25 for sparse, or cosine over embed for dense, and returns top 3 indices. A small test set mixes an order ID, a synonym-based medical need, and a GPU model. Averaging NDCG across these cases quantifies the policy's net effect. Emphasizing IDs helps exact lookups, while allowing semantics on open text needs. The printed average shows the combined strategy's overall quality and where the policy could improve. In a real project, you would map these pieces to existing systems. The BM25 scorer becomes your inverted index service. The embed step maps to a vector store or encoder, and the router can live in your query preprocessing layer. This toy test is how you sanity check behavior before scaling to a larger corpus. Recap in 3 points. What it is: a measured comparison of sparse term matching and dense semantic matching using a shared corpus and NDCG. When to use it: use sparse for identifier and model number queries, and dense for open-ended, synonym-rich needs. One caveat: dense vectors can overreach on exact tokens, so never assume embeddings replace exact matching without testing. Wrap punch. Next, tune BM25 parameters K1 and B on the sparse slice and measure NDCG changes, because small moves in those knobs often buy measurable gains on ID and product queries. If short, practical IR helps, subscribe and watch the IR videos.